Hi everybody and welcome. Today's lesson we're going to be talking about applications of exponential functions. So after watching this video we're going to be applying some of the models that we've studied the math of to real world contexts. So based off that real world context, I'm actually going to start this video off with a story. So this is a true story about an experience I had in college. So in college we lived in houses. So after your freshman year at Harvard you'd go to basically a big house for the remaining 3 years. And this was everybody on campus. So there was, I think, like 12 houses that you could get sorted into. And I got sorted into my house. And one of the cool things about my house was we had a guinea pig room. And this started, I think it was a few months after I moved in there. Someone decided that it'd be a good idea to put some guinea pigs in a spare room that nobody was using. So we started off with Maisie and Mochi were their names, two little pigs. So that quite literally was our starting point. So guinea pigs, and we'll say time. Well, it was a fun place to go. You're having a stressful day, hard time studying. You could just kind of go into this room. These cute little pigs that like to run around and they'd sit in your lap, and it would just be a good place to decompress. Well, one day came back and there weren't two pigs anymore. And not in a bad way. They were fine. They were healthy. We had four. And what somebody didn't notice is that Maisie and Mochi were not both girls. And I'll leave it at that. And guinea pigs did what guinea pigs do. And after that first unit of time, we had four guinea pigs in the room. And I don't know. Nobody calculated what was happening, I guess. I'm not sure. So we're like, okay, more pigs, more fun. Get a little bit more food, a little bit more bedding. It's fine. More to share. Well, you can probably guess after another period of time, we had some more pigs that appeared. And at a certain point, they had to take the pigs to the vet and make sure that this stopped happening. But you can imagine this model repeating itself. And true story, this actually did happen up to a certain point. After 8 pigs, we did cut it off. But if if it kept going, we could go up to our third time period. You could guess with that same model, we'd be looking at something like this. And at first it's like, okay, so like we added 2 pigs. And it's like, wow, there's 4 more pigs. This is a big deal. Time to stop this. And then if we didn't stop it, we'd be like, oh my gosh, there's 8 pigs. We're starting to fill up this room. And then by the time we get to 32 pigs, it's not so much as a floor, but just, a herd of guinea pigs that would slowly take over the house. So looking at this prediction is like, how are you so certain that, we're going to get to 32 pigs? Or the real question is, if we never stop this, when would the room fill to the roof with pigs? If we got to time 100, what is our value? And this is actually here the power of exponential functions. Based off of what we were just doing, you'd be like, okay, I'd have to plug in the value for 5, for 6, for 7. You have to keep doing that until you got to 100. Well, we're looking for a rule, something that's going to allow us to get to time 100 without having to monotonously punch all of these things into our calculator. So we actually have a form for this, our exponential form. And each of these things represents something that, we can plug in, we can figure out from what we have here. So this is our output value. This is going to be what we get based off of what's plugged in. Our x value here, this is over time. So our starting point is time 0. Our first guinea pig expansion, we can call it. It could be time 1, and that's kind of the idea. But what about a and b? So b is going to be what we multiply by. This is our rate of change. And I want to be specific with, that's what we multiply by. We're not adding here, we're going to be very specifically multiplying. And a is our starting point. This is kind of like our y-intercept. It's not a y-intercept, I want to be clear about that, but we used to talk about with our slope, our linear form, that we'd start somewhere. Well, this is going to be where we start. So in our pig example, we start off with 2 pigs. When I first moved in there, after a month or 2, and they decided a guinea pig room was a good idea for a bunch of college students to have, we had 2 pigs. Now, the difficult thing is, what are we multiplying by here? It's 2 times what? Is 4 times what that gets us 8? Is 8 times what that gets us 16? Well, in this case, we're going to be multiplying by, you can probably fill in the pattern, 2. Every single time, multiplying by 2. And then finally, x is our unit of time. So our full equation for this is going to look something like 2 times 2 to the x power. So we can't multiply these two together because that 2 is inside of the parentheses. It's protected by that exponent in PEMDAS. So again, remember that. We can't touch those. It's got to stay exactly like it is right here. So let's see, does this work? Is the function that we just made, does it fit our guinea pig expansion model? So at time equals 0, we plug in 0. Okay, so that's 2 times 2 to the 0 power is just 1. Okay, so far so good. 2 times 2 to the first. Okay, that's just 4. Okay, so far so good. Time period 2, 2 times 2 squared. Okay, 2 squared is 4, times 2 is 8. And it looks like this function model is going to work. So if we're looking for our 100, it looks like we could just have this equal to 2 times 2 to the 100 power. So after 100 guinea pig expansions, that's where we'd end up. And we can get an exact number for this. So we can see if this went untamed for a large period of time. We would have, oh my goodness, that is a very large number, 2.535 times 10 to the 30th power. That is a lot of guinea pigs. I should make sure I did that right. I'm going to punch this in one more time. 2 to the 100th power times 2. Yeah, that's it. So we'd move this decimal point over 30 times, and you'd see that would be a lot of pigs. We would maybe have the whole house filled or more with just guinea pigs. So that is what we're going to be looking at today, is you're going to have to find out what is our starting point, what is the rate, what do we multiply by, and then, X and Y are things that we get to plug in later based off of our unit of time. So a fun model today. There are a lot of fun examples of exponential growth. And again, these are the things. Let's go over one more example. I know the pigs was kind of a silly but fun one. We can do something like if we had 285 people to start, they subscribe to some sort of service. This service grows by 75% per year. And we want to know, after 9 years, how many people. All right, so if we're looking for each of our things, we start here. That's our starting point. So we started with 285 people. That's where we begin. Next, this is our growth rate. And the thing about this is it's growing, it's getting bigger. So it's not just 0.75, it's going to be 1.75. If we just multiply by 0.75, it actually go down. So for example, if you multiplied 285 times 75%, you would see a reduction. You would see like 214 or so people. But if you multiply 285 by 1.75, we see what we expect, which is just under 500 people. So that is a growth, not quite of double, but kind of close to it. So that's, again, why our rate here, if we're increasing by 75%, it's not 75, that'd go down, it's 1.75. So that's going to be our B. So we can make our equation and plug in what we have. So again, we start off with 285 people. Our rate is 1.75, and then our time period is some number of years. Well, here's our X value. They want to know after 9 years how many people. So 285 times that 1.75 growth rate to the 9th power, because it's over 9 years, it's going up exponentially. So 1.75, raise it to the 9th. Okay, multiply that by 285, and it looks like quite a few people 9 years later. 43,872. And I'm rounding it to a whole number because we can't have fractions of people. We have whole people, hopefully. So that would be the answer to this question. And again, we can't get there unless we start off with our form and we find our equation. So again, start with A, look for B, and then use those numbers of years to plug in for that X value. All right, so some more examples pretty similar to the second model that we just did. Again, focusing on the starting point, the growth rate, and then plugging in and evaluating for a certain number. Thanks for listening, everybody. Hopefully you enjoyed that. It actually is a true story. I'm not lying about that, about the guinea pigs and some good real-life applications of exponential